And I saw you doing the podcast. They should have said hi.
So we're now moving into the second section of CSE 260, which is going to focus more on sequential logic. The first section of the course, everything up until Exam 1, was focused primarily on combinational logic. And that's still going to come in handy for us as we go through the rest of the material. But sequential logic is a little bit different, so I think it's a good time to actually review what the difference is between combinational and sequential logic circuits. In a combinational circuit, basically every circuit we've seen so far is a combinational circuit, which means that the output of that particular circuit depends only upon the inputs that are going into that circuit. That is the definition of a combinational circuit. A sequential circuit also depends on the inputs going into the circuit, but a sequential circuit could also depend on past values of that circuit as well. So a sequential circuit, the output of that circuit is going to depend on past values as well as the current inputs. That's the main difference between combinational and sequential circuits. So with that in mind, we have an issue. If we're going to depend on past inputs, we need some way of remembering what those values were. We need some way of remembering what happened in the past. So we need some way of storing information. So the next few videos are going to talk about how we can store information in a logic circuit so that we can use that information in our sequential circuits that we're going to be creating. This video is going to introduce you to the concept of a latch. So a latch is a basic unit of storage in sequential digital logic circuits. Here is a picture of an SR latch. The SR stands for set and reset. You'll notice that the names of the inputs are also S and R, one for set and one for reset. Let's walk through this example and see if we can determine how this actually works. For starters, let's consider the case where S is equal to 1 and R is equal to 0. Now, you'll see that these, the outputs of these NOR gates are feeding back into each other. This is called cross-coupling. These are cross-coupled NOR gates, right? And so let's think about how that affects the operation of this particular circuit. If S is high and R is low, we know that this top NOR gate is going to be outputting a 0, right? You can just go look at the truth table for a NOR gate, you'll see that anytime we have a high signal coming into a NOR gate, that immediately tells us that we're going to be outputting 0 here. So that means down here on this bottom NOR gate, we have 2 zeros coming out, right? Which means that the output of this bottom NOR gate will be a 1. This 1 will be feeding back in. It doesn't really matter that this 1 is coming back into this NOR gate because we already know that the output is 0. But there's a couple of important things to pay attention to here. For starters, Q. The output of Q is equivalent to S in this case. S is high, right? Q will also be high. Another important thing to pay attention to is that this top value up here is the opposite of Q. In fact, this is often labeled as Q naught because whatever value you see up here at the top will always be the inverse of the output value of Q. So that's how it works when S is 1 and when R is 0. Let's consider what's going to happen then when I turn S to 0. So we were in the configuration where S is equal to 1 and R is equal to 0. Now let's consider what happens when I switch S to be low instead of high. Remember, I had a 1 here and a 0 here. I apologize, the diagram is labeled. But we have a 1 on Q and a 0 up here at top. Right? So when S goes low, what happens? Well, I still have a 1 being fed into this NOR gate. The fact that S went to 0 does not affect the output of this NOR gate. This is still going to be 0, right? And then down at the bottom, this NOR gate will now have a 0 and a 0 being fed into it. So that's going to lead this to sustain its output as well. This will output a value of 1, which is what it was in our previous condition. So what you'll notice is that when I switched both of these outputs to be low, when I switched both of these outputs to be 0, it simply retained the configuration that we had in the previous set of inputs. Let's try this again. This time let's set R to be high and S to be low. So if R is high, right, I know for a fact that this bottom NOR gate is going to be 0. right? This top NOR gate then will have 2 zeros coming in, which means the output will be 1. And in fact, you see the configuration that we have on this slide is exactly that case. I'm sorry, is not exactly that case. R will be 1, which means this will be 0, right? S will be 0, this will be 0, which means we have a 1 here. Again, we see Q naught is the opposite of Q. Now what happens again if we switch R and S to be both 0 in this particular configuration? Well, here, when we switch R to be low, it was high previously, it is now low, right? We see that, again, because I have a 1 coming in here and a 0, that does not affect the output of this NOR gate, right? So the output will remain 0, and again, this top NOR gate will have 2 zeros coming in, which means a 1 will be coming out. So that leads us to an interesting conclusion. The values that are coming out of this circuit when S and R are equal to 0 depend on the values that the circuit held previously. That's exactly what we're after. This latch is remembering the configuration that it was in previously. It's storing the information that it was in previously. So let's take a look at a truth table for this. That'll help make this a bit more clear. We see that if I have only S or only R high, right, that's going to dictate what's being stored in this particular latch. S is called the set input, so we're going to set this to be a high value. R stands for reset, which means set it back to be 0. So if set is high and R is low, I'm going to set this output to be a 1. And then if I switch my configuration back so that both inputs are 0, it's going to remember that it had a 1 coming out of Q previously. If I have my R signal high and my S signal low, that's going to reset this circuit. That's going to set Q to be low. And then when I go back to both inputs being low, it's going to remember the previous configuration and continue to output 0. Now there's one case that we haven't talked about, which is the case when both S and R are high, when they're both equal to 1. So let's think about what's going to happen in that particular case. In that particular case, we see that because I have 1s coming into both of these NOR gates, the output of both of these NOR gates is going to be low. Both of these is going to be low. You'll notice that breaks our rule. That breaks the rule that we had that stated that the top output here, this top wire, needed to be the opposite of the bottom wire, Q and Q naught. They're now both the same. So then let's consider the case when we go back to 0, 0 for S and R from that particular configuration. Remember, these are 0, 0 right now, and I'm going to switch S and R back to 0, 0, which we think should remember the previous condition of the circuit. So let's consider what happens. All of the inputs to both of my NOR gates will now be 0. I have 2 zeros coming from the right-hand side, S is 0 and R is 0, which means that the outputs of these NOR gates now become 1. So now I have 1 on both wires. But wait a second, these are cross-coupled NOR gates. So those 1s are actually going to be fed back into the NOR gates, and that means their output will then go to 0 again. Both outputs will then go to 0. But those will get fed back in, so the outputs will go back to 1, and those will get fed back in, so the outputs will go back to 0, and you get this oscillating effect. We have a name for this. It's actually called metastability, and it's an undesirable effect. We do not like this condition at all. So these inputs, where S and R are both equal to 1, where they're both high at the same time, has undescribed behavior, unknown behavior. It's undesirable. We do not use that configuration of this circuit. It's not allowed for us to use that particular configuration. All right, just to wrap this video up, typically I will not draw out the gates of my latches every single time I need to use them. So to make things simpler, we have a component diagram for our latches. We're going to see another example of a component diagram for some different kinds of latches on the next video. But here is the component diagram for an SR latch. We see S and R coming in. and Q coming out. Sometimes you will see Q knots coming out here as well. You oftentimes don't necessarily need Q knots, so it might be omitted as it is in this particular case. In the next slide, we're going to revisit this metastability problem and see if we can't design a better latch that could potentially fix it and make our lives a little bit easier.
Did I welcome in Blazemonger 2 months